Hello and welcome to day 2 of chapter 7 and our last day. So as I've said earlier, we've done stoichiometry throughout the course. So now that we get to chapter 7 on stoichiometry, we're just going to review because it's really important for Chem 30. So a review is justified, and I feel like you're a little bit rusty on your stoich, especially gas stoich, because we haven't done it for couple months. I think it was one of the first topics we learned when we went online. So you've learned 3 types of stoich, and you guys have your notes to follow along. We're going to do, normally I only do 4 questions, but today I'm offering you a special deal, 5 for the price of 4. So we're going to look at 5 stoichiometry problems today, and they're going to be a mixture of mass, gas, and solution stoich. So as it says on the screen, you're going to use a balanced chemical equation. You will be given a mass of a solid, a volume of a gas, or a concentration and volume of a solution. Those are always your starting points in stoichiometry. A mass for a solid, a volume for a gas, or a concentration and volume of a solution. That's your starting point. From there, you can use stoich to find any mass of solid, any volume of gas, or any volume or concentration of solution. So we're going to be looking at all 3 of those methods today, and we're going to do some mixtures where you have a combo of those methods. How exciting is that? Okay, this is not cooperating very nicely. There we go. Okay, so first problem we're going to look at is gravimetric or mass stoichiometry. We did a bunch of these early on. These were the first ones we did. So determine the mass of precipitate produced when 3.5 grams of potassium iodide in solution reacts with lead 2 nitrate. Lead 2, so we'll need 2 nitrates. It's also solution. Okay, so we get double replacement PbI2, and that one's low solubility. If you looked it up on your solubility table, you would see that iodide right here with Pb right there is low solubility or solid. And KNO3 is high solubility, so it's aqueous. States aren't critical to the math, but we should still write proper balanced chemical equations. So there it is, balanced. Balancing is really important. 2K, whoops. 2I, 2NO3, 2NO3. Okay, we're good, we're balanced. That's really important. Okay, determine the mass of precipitate. So there's the precipitate. That's why we needed our states, because this one is not a precipitate. It's aqueous. Okay, so we're looking for the mass of PbI2 solid. So what did they give us? 3.5 grams of this one. 3.5 grams of Ki. So in stoichiometry, when you're trying to find an amount of another chemical, and then so a mass, a volume, concentration, your goal in stoich is always find the moles of something, because once you have found the moles, we can use these coefficients to turn moles of any one chemical into moles of any other chemical using the molar ratio. And that's the heart of every stoich problem. So let's find the moles. How do we do it? Well, we have the mass of Ki, and we have the molar mass of Ki. I'm just going to write these. I'll put them down here. We need the molar mass of potassium iodide. And that is, where did I put it? 166.00 grams per mole. We're also going to need the molar mass of what we're looking for, the precipitate, PbI2. And that one is 461.00 grams per mole. Okay, so when you're dealing with gravimetric or solids, you need the molar mass of the chemicals that you're looking for or given, because that's how we're going to get the moles. And we're always trying to find the moles. Okay, so let's find the moles of PbI2. So I have the molar mass of PbI2. Let's flip it so that we have moles on top. 461.00 grams on the bottom. We multiply by the mass of Ki. Oh my gosh, I used the wrong one. Back up. Okay. We have moles of Ki. My apologies. So we're using Ki. 166 grams per mole times the grams. And if you want, you could put grams of Ki. And then up here, you could put 3.5 grams of Ki. I usually don't put this one. And that way, when I cancel out my grams, I am left with moles of Ki, which is what I was looking for. Mass times molar mass gives you the moles of the chemical. And we're looking for potassium iodide. So that was molar mass of potassium iodide times mass of potassium iodide. Okay, so I have the moles of Ki, and now I'm looking for the precipitate. So we use our molar ratio. I'm going to flip to purple for this since I underline those in purple. So we are looking for 1 mole of PbI2 is formed for every 2 moles of Ki that are used up. Okay, so now what can I cancel out? The Ki's. So if I quit right now, I have solved for the moles of PbI2, and we want the mass. So my last step is molar mass of PbI2, and that's this 461.00. What a mess I'm making. Grams per mole. This thing is in the worst possible spot. It was not very good planning on my part. Saw my written work always looks messy. Okay, so canceling out, what else cancels out in here? So now those moles cancel out, and all I have left is grams of PbI2, which is what I'm looking for, the mass of PbI2. So there's my units, and there's my formula that's left. So now it's just a matter of doing the math, and the math will be 3.5 times 461 divided by 166 times 2. So multiply the numerator, divide it by the total denominator, and you get 4.859. And sig digs, 2 sig digs is our lowest, so 4.9 grams. 4.9 grams of PbI2. Let's see if I can be a little neater on the next one. This one's a bit of a disaster. Okay, so that's gravimetric stoich, mass to mass. Okay, given a mass, determine a volume of gas. Okay, determine the volume of oxygen produced at 20 degrees Celsius. So here's our gas part, 96 kilopascal. Here's our mass of mercury 2 oxide. So we're starting with mercury 2 plus, oxide is a 2 minus. We're starting with solid mercury oxide and decomposing it into its elements. Oxygen will be a gas. Mercury is one of the 2 liquids. Balance it. Okay, so remember you always have to start with a balanced equation. So there it is. Okay, we're looking for the volume of oxygen, gas. But we have to start with moles, and we can get moles from this mass. So that means I'm just going to write off to the side. The molar mass of mercury oxide is 216.59 grams per mole. Okay, so I want the moles of mercury oxide, and I can get it from right there. So I'm going to flip that. Moles over 216.59 grams. Times the 5 grams of HGO. And I like to write the formula there because now when I go to cancel out my grams, it tells me I have just solved for the moles of HGO. Good. Okay. So we have the moles of mercury oxide, but we're interested in the oxygen. So here's where our molar ratio comes in. 1 oxygen is produced for every 2 HGO. Remember, the one we want to cancel out, the HGO, has to go on the bottom. So now they cancel out. And if you look at our units, we've now solved for the moles of oxygen. We're getting close because we want the volume, and it's a gas. So now we use our gas chemistry. We have moles, and we want liters. Remember this guy? 8.314 kilopascal liter over mole Kelvin. There's your conversion unit for all the gas problems, the ideal gas constant. And we're looking for volume or liters, so we're going to write that on top. 8.314 kilopascal liter over mole Kelvin. Okay, time to see what cancels out here. Moles cancels out. We're looking for liters of oxygen, so we want to keep those two. So I have to get rid of kilopascal, get rid of Kelvin. Okay, kilopascal on top. So I'm going to write this 96 kilopascal on the bottom. And they're gone. And Kelvin on the bottom. So I need Kelvin on the top. 20 degrees Celsius. Add 273 to convert it to Kelvin. And we get 293 Kelvin, no decimal places. Okay, Kelvin's gone. All my units cancel out except liters of O2. It's amazing. So when I'm done here, I will have liters of O2 gas. So it's going to be 5 times 1 times 8.314 times 293 divided by the bottom in brackets, 216.59 times 2 times 96. And you do all of that and it works out to 0.2928 liters. And we have 3 sig digs, 0.293 liters of O2. So that's called a mixed stoich problem. Start with a mass and go to a volume of gas. So it's gravimetric and gas stoich. Hopefully this is coming back to you. For some of you, you love stoich. This is easy. Today's like a freebie lesson. Nice light review. Others, this is another chance to grasp stoich if you didn't get it the first or second time around. Okay, so now we're going to go the opposite. Given a volume of gas, determine a mass. Okay, well, we need our balanced chemical equation. BCE, balanced chemical equation, before Common Era. When I was in Thailand, my cell phone, the entire calendar flipped on my cell phone. It was the weirdest thing. In Thailand, they have 2 systems of time. They have the BC AD, but they also have, how did it go? It had Buddha in it. It was their second timeline was based on when Buddha was born. And to them, Buddha was an actual living person who was born and became a god, a deity. And it was about 4 years off of the birth of Christ, before Christ era. And so my calendar, everything on my cell phone was off by like 4 years and 2 months. And I was like, what is going on? And it was a slightly different, it's like BBE or something, before Buddha era. It was really weird. And it just happened for a day and then it went back to the proper setting. So interesting. I learned a little bit about Buddha. Okay, how's that for getting off topic? Okay, so we are looking for grams of water vapor produced when propane is burned. Propane, probably don't remember that formula, C3H. How many H's? 8. Burned, what does that mean? It's reacting with oxygen gas. And when you burn a hydrocarbon, you get H2O. The hydrogen goes with the oxygen and the carbon goes with the oxygen. This is burning in an open system. It's producing 2 vapors. We just need to balance it. 3 carbon, 8 hydrogen, 8 hydrogen. 4 and 6 is 10 oxygen. 5 times 2 is 10. Okay, so there's our balanced chemical equation. How many grams of water vapor? Mass of H2O vapor. Okay, it's stoichiometry. We're trying to predict an amount of a product, so we're going to need moles. Where do we get moles from? From here, we have 20 liters at 20 degrees Celsius and 1,000 kilopascal. 8.314 kilopascal liter over mole Kelvin. There's our moles. So we have to flip our ideal gas constant. Mole Kelvin on top, 8.314 kilopascal liter on the bottom. Okay, let's cancel out. We can get moles of propane from this by canceling everything else out. So Kelvin is on top. So let's put it on the bottom. 293 Kelvin, gone. Got to get rid of kilopascals and liters. 1,000 kilopascals on top, cancels with kilopascal on the bottom. And 20 liters on top, cancels with liters on the bottom. And let's put 20 liters of propane. So we introduce our formula. So right now, all I have left is moles of propane. So we used gas stoich to get our moles of propane, but we're interested in mass of water. So you have to convert propane to water. Put the chemical you're looking for on top. It's molar ratio. So 4 moles of water react for every 1 mole of propane that's used up. Propane goes on the bottom so that these cancel out. So if I quit right now, I have solved 4 moles of water, and we want mass. So we're not quite done. We have to convert moles to mass using molar mass, and the molar mass of water is 18.02 grams per mole. Moles cancel out, and now we've introduced grams of water. So when we solve this, we will get grams of H2O. Everything on the top multiplied by everything on the bottom, and we get 592 grams of water. 3 sig digs to match 3 sig digs in the question. Okay, so that's a mixture of gravimetric and gas stoich. 3 down. Remember, you get 5 for the price of 4 today. 2 left. Okay, in an experiment, so now we're doing solution stoich. 10 mils of sulfuric acid reacts completely with 15.9 mils of 0.15 mole per liter sodium hydroxide solutions. We have 2 solutions. NaOH reacting with sulfuric acid, H2SO4. That's one of the big 6 strong acids to produce double replacement. Na2SO4 and HOH liquid. And when we go to balance it, we need a 2 in front of there to match 2 sodium, 2 hydroxide, 2 hydrogen. We're balanced. Okay. So how do we start this one? Calculate the amount concentration of the sulfuric acid, concentration of H2SO4. So we want the concentration of this one. Okay. They've given us the volume and concentration of the sodium hydroxide. So that's your starting point. If we put the moles on top, 0.150 moles per liter of NaOH times its volume, 15.9 mil of NaOH. So these are both NaOH, and this is important. It's always concentration times volume, or moles per liter times liters to get the moles. So we've got the moles of NaOH, perfect. But we want the concentration of sulfuric acid. So we got to turn moles of NaOH into moles of H2SO4 using our molar ratio. 1 H2SO4 for every 2 NaOH. Okay, so now if I cancel out my NaOH, we're going to pretend that one wasn't there. I'm going to have this is milliliters, and this is liters. So I'm not going to cancel those out yet. They kind of do, but we're going to be left with millimoles. So we'll just hold off on that. So the last thing we need to do is divide by the volume of H2SO4. Because right now we have the moles of H2SO4, and we want the moles per liter. Now, I didn't convert both of these to liters, and the reason I didn't convert them is the milliliters cancels out. So it saves you a little bit of converting. So milliliters here cancels out with milliliters there. So now my final unit is moles per liter, H2SO4. H2SO4, which is what we're looking for. Okay, multiply everything on the top, divide by everything on the bottom, and you get 0.1193 sig digs moles per liter of H2SO4. So that is a standard solution stoich problem. Concentration times volume to get the moles, molar ratio to convert it, and then divide by the volume to get the moles per liter. Boom. Okay, last one. This one is a combination. We're going to do gas stoic and solution stoic. Ooh, what a deal. Okay, so balanced chemical equation first. Zinc metal is added to sulfuric acid. This will be a single replacement to give us zinc sulfate and hydrogen gas. Often when you add metals to an acid, you get hydrogen gas. Okay, so we need to balance it, 2 hydrogen, 2 hydrogen. Oh, it's balanced. Wow, okay, that was easy. All right, so that was a single replacement. And now what are we looking for? What have we got here? We have a volume and concentration of H2SO4. So there's where we get our moles from. And we're looking for the volume of hydrogen gas. Volume of H2 gas. Okay, so moles first. Put the moles on top. Times the liters or milliliters of H2SO4. Okay, so just for fun, I'm going to cancel out the liters, but leave the milli. So right now we've solved for the millimoles of H2SO4. We need to convert that to hydrogen. We're looking for hydrogen. 1 hydrogen produced for every 1 H2SO4 that reacts. Okay, I'm going to switch up my colors and do some canceling here. So the H2SO4s are gone. So now I have solved for the millimoles of hydrogen. And we want the volume, and it's at STP. Remember when you see STP, that means that for every gas, it occupies 22.4 liters per mole. Okay, so there's how we're going to turn our moles into liters. So I want to put liters on the top, 22.4 liters, and mole on the bottom. Moles cancel out. Now, what do we have left for units? Pay attention to this. We've got milliliters of hydrogen. So I didn't cancel out that milli. I just left it in there because I knew my final answer would be a volume in milliliters. Volume equals everything on the top divided by everything on the bottom, and we get 73.92 milliliters, 3 sig digs, 73.9 milliliters of hydrogen gas. If you had converted this to liters, your final answer would be 0.0739 liters, which is the same thing, just not in milli. Okay, yay. Dun, 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 dun. Dun, dun. Not very happy. He should be. Tough lesson today. Lots of content, lots of math. Tomorrow, super easy. The first lesson of chapter 8 is crazy easy, and then it picks up from there. So I guess it's that tomorrow. I don't think so. Anyway, we'll see. Your assignment for this one, I'm not sure I put it in here. I did not, so I'll put it in your description for you to practice your stoichiometry. Okay, have a good day, and I will see you soon.